All right, so let's have a look here at the sample questions, which I've conveniently typed out for you. I've eliminated some work.
Actually, it's gonna work.
No, it's not work. It's not work.
Well, by typing it probably works.
Well, you're pushing that key up and down, so yeah, you're applying a force. That is work. Right? Is writing work?
Yeah, because you're pushing force.
You're pushing it sideways. Yeah. I think against friction. Yeah, you'd be doing some work when you write.
Yeah, we're pushing down.
Yeah. Okay. So how much work? What about work against friction? How much work is done when sliding a 30-kilogram chair a distance of 50 meters across a rough surface where the force of friction is 50 newtons?
Let's see, does the force of friction actually matter?
It does. Oh, what happened there? That was not good. Oh, do I only have one slide? Well, that's kind of lousy. That's not going to be that's not going to be a very good PowerPoint, is it? All right. Well, I'll just have to do it here, I guess. Okay. All right. So we got our chair, which I will show as a box. Here's question number 1. It's 30 kilograms, right? I'm moving it 15 meters. If my force of friction is 50 newtons, it doesn't say at a constant speed, but it doesn't give me a speed. So what's my likely yeah, I don't know what I was trying to say there. What's my likely applied force is going to be 50 newtons. So work equals FD. Does the mass of the thing matter? No, in fact, it's built into the 50 newtons, right? Right? FF would be mu Fn, mg. It's built into that 50. So it's just going to be 50 newtons times 15. 750, right? 750 joules.
Joule, J-O-U.
Capital Joules. You would be. Just put a capital J. Yeah. 750 joules of energy. Now, generally, oh, did I just break that string? No, it's good. Generally, like when you're reading your vector serial there, it would talk about kilojoules actually. Like 750 joules isn't a lot of energy.
Do you know what you just said? When you're reading your vector serial.
Box.
Why? It's actual why.
It measures on the vector serial box. It measures the energy of the serial in joules.
I actually heard you right. Oh my God, seriously?
It's the only food product I've ever found that has it measured in joules.
I thought you were just being funny.
No, I'm not always funny.
Well, I just, what I am.
You might think I am, but I'm not always funny. What about work done against gravity? How much work is done in lifting 2 bricks, each of mass 1.4 kilograms, from the floor to the top of your table at a distance of 80 centimeters? Now, does my 80 centimeters have to be in meters?
Yes.
Of course it does. We know that now. So my distance is 0.8.
So 8 force.
Though, yeah, we're lifting against the weight force here, right? So I'm going to have 2 times 1.4 times 9.8. Two times 1.4 times 9.8, or 27.44 newtons of force. Now W equals FD. Distance 0.8, and you could probably do this all in one step if you want. 22.
That's not a lot of work.
No,
So can you figure this out for everything?
pretty much. In fact, when I show you, Quinn, and I'll get to this, because energy, like if I raise something up, I can calculate how much potential energy it has. And knowing that, I should be able to calculate how much kinetic energy it should have when it's done falling, and I can tell you how fast something's going. Say, for example, if you happen to be at Canada's Wonderland and you're looking at a person up on a ride, and you can estimate how big they are and how high they are, you could figure out how fast they'd be going at the bottom. You could do that all in your head and annoy the people around you.
Have you ever done that?
Yeah.
That's really funny.
My son says, "How fast do you think they're going, Dad?" I said, "Well, let's see here. They're about maybe when we weigh about this. Maybe we go going this fast at the bottom." And my wife just shakes her head and goes, "I can't believe you did
Yeah.
You are.
that." Yeah,
Yeah. With pride.
I say it with pride. I can't believe you know how to do that.
What's that?
I don't know. That's customizing my toolbar. I want to do that. What about number 3? A 1.5 kilogram Dynamics cart being pulled at an angle of 30 degrees above the horizontal with a force of 25 newtons. The cart moves 4 meters. How much work was done on the cart? I think we're going to have to draw this one out here. So it's being pulled with 25 newtons. The angle is 30 degrees. The distance moved is 4 meters. And the mass is 1.5. Does the mass matter here? I got my distance. What I really need is I need the force. I've got the force. What about the angle? Does the angle matter? Why does the angle matter? Because you need to find just just Fx, so just the horizontal component. So first step would be to say Fh is equal to 25 cos 30. Cos 30, which is 21.7 newtons. And now just W equals Fd. 21.7 times my distance of 4 meters. 86.6 joules. These are pretty easy questions, aren't they?
No, it's pretty.
Well, they're obviously going to be. Yeah.
It's always not.
But if you're carrying a box, isn't it acting as air resistance you're pushing?
Yeah, there you might do a small amount of work to overcome air resistance.
If there's frictionless, though, then.
But if you're a skinny bald man, there's not a lot of air resistance on it.
Skinny ball, but can't read it. Say read this late for play, but.
Mm-hmm. How about you guys try this one on your own? No?
Okay, I'll let
30 kilograms.
Very good.
We got 6 meters here, 3 meters there,
Oh, wow.
30 degrees.
Oh, my God.
But give that a try. See what happens.
Oh, rubber work.
You got a whole. Quickly. So how much work is done to pull the cart up the plane? So we've got an applied force up, but what's it working against? Does it say frictionless?
Downforce.
Doesn't say any, downforce, exactly. So FD, you'll remember, is mg sine theta. Isn't it nice how we keep coming back to some of these old formulas so I can kind of like review for the exam as we go?
What about the triangle thing you said 7?
Well, that's what I'm talking about here.
No, that's MG sine theta.
Well, Stefan's just talking about, he's just talking about this triangle, isn't he?
Yeah, the one that goes down, like the downforce.
Well, yeah, then there's like, you mean this one?
No. Draw like underneath the block.
Yeah,
Draw it down.
Yeah, you got to triangle against theta.
Yeah, that one.
yeah, same thing. This is FD, right?
Okay, what's the other one?
F perpendicular, or F normal,
Wait, what's
is weight force, yeah.
okay.
So FD is mg sine theta. So in this case here, we've got a 30 kilogram block times 9.8 times the sine of theta. 147, right, Quinn?
Right.
So 147 newtons of force is the amount of force needed. So that means that the work done is my 147. The distance up the ramp is 6 for a total of 882 joules.
All it takes to push a plane.
Up the ramp. Now that's if it's frictionless, right?
Got a triangle and just hover.
Now what if you just lifted that thing straight up to the top of the ramp?
Not lift the plane.
No. The plane is the ramp. It's not like an aeroplane.
Oh.
Arrow bar?
Yes. Well, they're light because they got bubbles inside.
Alright, bubbles. I'm gonna go up and see it.
Okay, so in part B here, the work done is Fd. In this case, it's against gravity, so our formula mgd. 30 kilograms times 9.8 times the distance up is 3. Guess what you get?
147.
Exactly the same. How come? Because it's got the same amount of potential energy at the top, whether you pushed it up the ramp or you just lifted it there.
So really?
Same amount of work.
That's if it's frictionless.
Frictionless. Same amount of work because it has the same potential energy at the top. Now, which one is easier? Even if it's frictionless, which one's easier? Pushing up the ramp. How come? Less force, right? The trade-off is it's less force, but over a longer distance. Exactly, Scott. Now, as Quinn has aptly pointed out, there is friction here. So how much work is done if there's a friction force of 50 newtons up the plane? So you're going to need my applied force is going to have to be I better write it up better here, is going to be my down force plus my friction. So in other words, 147, that should be a plus, plus another 50. You're going to need 197 newtons of force. So yes, that's going to be more work. Fd,
with friction.
197. This is with friction. Our distance is 6 meters. So it's going to be 1,082 joules of work. Where does the extra work go? Heat. Exactly. Okay, it's going to be warmer because of friction. It's going to be warmer at the top than it is at the bottom.
That actually makes sense.
Yeah, it makes clear. There's nothing to it. Right? Okay, so what have you guys got for more sheets there? You got anything else? Oh yeah, you do have some. Okay, so you've got some problems there, I think, right? Well, so tomorrow will be a little bit of a work period to work on some work problems. Anyone that wants to run up the stairs may do so. I'll hand out the personal power lab right now, and maybe I'll even talk about it for a second. Okay, so the personal power lab, blah, 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 you guys can read it. Basically, you're going to determine your horsepower, your power rating by running up the stairs. You have to do work by running up the stairs, work against gravity, right? So you need to figure out how much you weigh. I have scales here, measured in newtons actually, right? You've seen them. So we don't have to, if you want to convert, find how much you weigh, then that's fine. But we'll leave it all in newtons, right? About the third paragraph there down, a person is a machine which also has a power rating. Some people are more powerful than others. That is, they're capable of doing the same amount of work in less time. In this lab, you will measure your own personal power by making measurements as you climb a flight of stairs within your home or obviously school. You will present your results in the form of a video. Pretend that you're creating a video for students to learn about power. So you may want to, as a group, delegate jobs and video parts to individual members. I suggest Movie Maker, PowerPoint can be used, any video editing software is fine. Okay, just make sure you know how to do those details before you spend hours filming. Not hours, but minutes. Okay, there's a checklist there. Okay, what you have to include. Okay, I also want this sheet handed in as well. Okay, it's pretty straightforward. Everyone has to do it. In the on the second page here, you need to do all questions 1 to 5, but I only need to see one done in the video. Okay, you've got to do them all. Pick one that you want to do and do that in the video. Okay, on the back side, I think it says, yeah, I want you to do questions 6 and 7, but again, only one has to be in the video.
1 of 6 or 7, or 1 of 7?
No, 1 of 6 or 7. Yeah, 2 questions in the video. 2 questions in the video. Now you'll notice there in 7 they talk about vectors. So there you go. There's the proof. Vector has 900 kilojoules of energy in a bowl. There's Raisin Bran on the right. In calories, you have to figure out what it is in joules. Just for fun. Well, I want you to know how long you have to climb the stairs to burn off a bowl of Raisin Bran. I think you'll be surprised. There's a rubric on the back. I would suggest that you use it to keep track of, yeah, we did all that, so we were going to get 30 out of 30. It's worth 10%, yeah. But it's easy to get 30, you just got to do it up.
Pro.
Just do the lap, do the miles.
So like if I'm at 80 right now,
3 is probably good. 3 or 4, like 4 is absolute max.
so if I'm at 80 right now, I do that, I get a 90.
Wow.